6.1a, we're going to compute the probability of a single simple event. Here's a scenario. Consider the experiment of tossing a pair of fair six-sided dice. Find the probability that the sum of the numbers that are face up is at least 9. So what I'm going to do here is actually draw out the sample space first. So for the first die, we can have a 1 through a 6. So I'll jot those down. And for the second die, we can have the same scenario. So if you look at the picture of the sample space, there's going to be 36 different possible outcomes. They want the ones where the probability of the sum of the numbers on the faces is at least 9. So that means it can include 9. So I need numbers 9 on up. So I'm going to go in and just put X's on all of the totals that are 9 or higher. And you're going to notice I marked these 10. So here we have a 6 and 3, and we also have a 3 and a 6. We have 6 and 4, 6, 5, 6, 6, and these other combinations. So if you count that, there's going to be 10 out of 36 as our answer. So 10 over 36 is an appropriate answer. We can simplify the fraction though and divide a 2 out, so there would be 5 out of 18. 6.1b, they want to list out the sample space or the outcomes. So consider the experiment of tossing a four-sided die followed by flipping a coin that has labeled an H and a T. Write out the sample space for that. I'm actually going to show you a grid of it first, and then we will write out the sample space. So the grid on this one, we have a four-sided die, so it would be 1, 2, 3, and 4. And then the choices we have on our coin are heads or tails. If you look at this grid, you can tell that there's going to be 8 possible scenarios. And again, you can get that by saying we have a four-sided die and a two-sided coin, so 4 times 2 is going to give us the 8 scenarios. So let's write out these different 8 scenarios for this entire sample space. And when you do that, these are the 8 that you're going to get. For example, we're just going to do 1H, 2H, 3H, 4H, and then the T's. The second part here says list the outcomes for the event where it's an odd number and a head. So all I'm going to do is go back to my entire sample space and look at the ones where there's an odd number and a head. And I can tell here there's only 2 scenarios. It's a 1H and a 3H. And there I listed the outcomes. Be careful, they did not ask me for the probability. If it was the probability, it would be 2 out of 8. They actually just wanted them listed. 6.1c, we need to understand the difference between probability and relative frequency. So here it says, given there are 8 cards in a hat numbered 1 through 8, an experiment is done 6,600 times and the table shows the results. So here's all of the possible outcomes for the 8 cards. So what they did is they had the 8 cards in, they drew one out and recorded it and put it back and drew it out again 6,600 times. Compute the probability and the relative frequency of drawing a 5. Assuming these cards are fair and of equal size, the probability of actually pulling out a card number 5 out of 8 cards would be 1 out of 8 is the true probability. There's 1 chance out of 8 that I get the 5. However, the frequency on this one, when they did the experiment, it actually happened 1,005 times out of the 6,600. So the frequency for relative frequency is 1,005 over the 6,600. Now to make them comparable, I am going to change them to decimals. 1 over 8 is 0.125. Helps me understand that a little bit better. And then 1,005 divided by the 6,600 is going to actually give me 0.152. These are actually pretty close, but in theory we would expect this to happen 12.5% of the time, but in an experiment it actually happened 15.2% of the time. So probability is what we theoretically expect to happen. However, when you do an experiment, the relative frequency is what actually happened. In 6.2a, we're going to understand union, intersection, and mutually exclusive events. Here we have the probability formula. It's the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Here it asks, indicate which component in the formula represents union and which represents intersection. Now, if this formula had been written with the notation of union and intersection, here's what we would have seen. Remember, the word or is the union sign, and it looks like a U. The word and is the upside down U, which means the intersection. So the union is represented by the A or B, or in this case, is a symbol, that one. The intersection we can actually see as the and words. So this means intersection, or in symbol format, this one means intersection. If we were to sketch the Venn diagrams for that, we would have something like this. Remember, if it says A or B means everything in this entire range. But A and B has to happen. A and B happens where it actually intersects. So the intersection here is the probability of A and B. The next question, if events A and B were mutually exclusive, which component in the formula would not exist and why? What you want to remember is what mutually exclusive means. It means they have nothing in common. If two events have nothing in common, then the probability of both A and B happening at the same time is actually impossible. So what's going to happen is the probability of A and B will equal 0 in this case if they're mutually exclusive. So that means if two events are mutually exclusive and have nothing in common, then the intersection of those two events can never take place. And that Venn diagram would actually look something more like this, where you have two circles, A and B, and they do not intersect. This is a picture of mutually exclusive. So knowing that mutually exclusive means nothing in common, let's look at 6.2b. Find OR probabilities with two events that are mutually exclusive, which means they have nothing in common. And we already have defined the OR probability up here. So what we know for this formula is it's going to be the probability of A or B is going to be equal to the probability of A plus the probability of B. However, because they're mutually exclusive, it says here there's nothing in common, this probability can never happen, so I can disregard it. However, I sometimes like to think about it and just double check that that's true, and we'll do that this time around too. Now for this problem to be truly mutually exclusive, I need to adjust this part right here. We're going to change this word that says second here to first, and I'll read the question. A fair spinner with 6 congruent sectors numbered 1 through 6 is spun twice. What is the probability that the first spin is a 4 or the first spin is an odd number? So I'm just going to write this out in our probability format. So what we have, what's the probability the first is a 4 or the first is odd? Would be first find the probability the first is a 4, add to it the probability the first is odd, and then subtract if the first is a 4 and the first is an odd. Keep in mind an OR probability in most cases always means to add and not to multiply. So let's go ahead and do this. The probability that the first spin is a 4. Well, there's 6 outcomes on the first spinner, so the probability that it's a 4 would be 1/6. Then I'm going to add to it the probability that the first is an odd. The numbers 1 through 6, 3 of those are odd, so that would be 3 out of 6. And then I'm going to double check and subtract this from it. What's the probability the first is a 4 and at the same time the first is an odd? Well, the number 4 is not an odd number, therefore these two events at the same time can never happen, which means they are mutually exclusive. And that would be a 0 probability. So if you add this together, it's going to be 4/6, which would simplify to 2/3. 6.2c and d are together because you can use either approach. We're going to continue to find OR probabilities with two events, this time that are not mutually exclusive, which means this probability right here will actually exist. What we also can do though is apply a counting principle to two events that are not mutually exclusive if we prefer to do that. So we can do the formula or we could draw out the sample space and count. We're going to continue with the same scenario. A fair spinner with 6 congruent sectors numbered 1 through 6 is spun twice. Here's the question. What is the probability the total of the two spins is 8 or the second spin is a multiple of 2? So let's write the formula out and see what that looks like. So the formula would read, what is the probability the sum of the two is 8, or the second is a multiple of 2. Just break it into this. First find the probability the sum of the two is 8, add to it the probability that the second is a multiple of 2, but then subtract out if both can happen at the same time. That is, the sum of the two is 8, but at the second time, the second multiple is a 2. So I'm going to draw the sample space for this so we can see it better. So what we see here is the options for spin 1 and spin 2. Again, there's 6 and 6, so if we multiply 6 times 6, we get 36 possible outcomes, which is what you see here are 36 different spaces. So let's go ahead and do this probability. Let's check off the ones where the probability of the sum is equal to 8. We know that 3 and 5 and 5 and 3 will be 8, and so is 4 and 4. Also, 6 and 2 and 2 and 6. So that gets us 5 out of 36 meet that requirement. Now let's look at when the second spin is a multiple of 2. If we look at that, a multiple of 2 would be the 2's would work. Could have a 4 and a 6. And if you look at that, we're going to end up having 18 out of 36, or 1/2 meet that requirement. Now let's see if we have to subtract out any that have the probability where the sum is 8 and at the same time the second is a multiple of 2. Basically, we're looking if there was any overlap or intersection. If you look at it, the sum is 8 and the multiple is 2, would be 6 and 2. Another one would be 4 and 4, and the other one here is 2 and 6. So if we notice that, 3 out of 36 are actually double counted, so we have to subtract them out. So to finish up the problem, let's do 5 plus 18 minus 3. That's going to give us 20 out of 36. We can further simplify that by pulling out a multiple of 4, which would be 5 over 9 as our final answer. 6.2e wants us to state the complement of an event. So if I go to Culver's, I can choose to order a hamburger, chicken sandwich, or fish sandwich. What is the complement to ordering a chicken sandwich? Well, the true complement, you would say, is not ordering a chicken sandwich. In the key here, all I did for complement was change it to not. And another way we could look at it is not ordering a chicken sandwich would also mean just ordering a hamburger or a fish sandwich. Now, 6.2f, compute probabilities of events that are complements of each other. So here we have event A and B are mutually exclusive, which means they have nothing in common. So that means the probability of A and B would be 0. They're telling us the probability of A is 0.6, the probability of B is 0.1. Find the probability of not getting A or B. So the easiest way to do this for the complement is remember this formula. If you're asked to find the complement, for this case not, but I'm going to say the probability of not A, to find the probability of not A, all you do is take 1 minus the probability of getting A. So what I'm going to do for this is, why don't I just go ahead and find the probability of A or B. If I find the probability of A or B, I can then take this and then subtract it from 1 to get the not component. So this is the formula I just stated. To find the probability of not A or B, let's just do 1 minus the probability of A or B. So let's find the probability of A or B. Don't forget, the probability of A or B just means to add. That's the trigger for OR. Now, they are mutually exclusive, so there's nothing in common, so I do not have to subtract out the probability of A and B. If we finish this, we know it's 0.6 plus 0.1, so the answer here is 0.7. But what I just found was this. So I have to come back, and what I do is I'm going to take 1 minus 0.7. The answer here, therefore, ends up being 0.3. And we're done. 6.3a and 6.3b compute the number of arrangements by sketching a tree diagram. Then I'll also show you how to compute the arrangements using the multiplication counting principle, which is more common because it's quicker. Here we have how many different outfits could you make from 3 pairs of pants, 5 shirts, and 2 pairs of shoes. Sketch the tree diagram and do the counting principle. So I'm going to start off with the fact that I have pants. So I'm going to have, my first choice is, I'll just call it pants 1, pant 2, or pant 3. After that, I have to decide on a shirt. So if I chose to wear pants 1, I now have 5 different shirt choices. So I need to branch that out 5 times. I'm therefore going to have to do this because if I chose pant 2, I could have chose now 5 different shirts again. And if I had chosen pant 3, the same thing. There's going to be 5 different choices. Now after I make that choice, I now have to pick a pair of shoes. So if I chose pant 1 and shirt 1, I now have to choose what type of shoes I want. And from here, there's going to be 2 choices for shoes. What if I chose pant 1 in this second shirt? There's still going to be now 2 shoes. So all of these branches are going to have 2 pairs of shoes coming back at the end. So if you draw those all in, it gets a little busy and involved here. But if you do that, and if you were to add all of the branches we made, because here's one branch right here, here's another branch, all of these extensions are their own branches. If you count all these branches up, you'll get the answer. But the multiplication counting principle is more likely used. We're going to have to make 3 choices: a pair of pants, a shirt, and some shoes that I want to make. Remember, you just put how many choices you have. Here we have 3 pairs of pants. Here there are 5 shirts, and there's 2 pairs of shoes. If you multiply this together, you're going to get 30. If you were to add up all of these branches, you will realize that there actually are 30 different branches. Therefore, you can get the same answer. Now, if you had to do this on a test, you would have to make sure that these branches were all labeled. So don't forget to say that this would be shirt 1, 2, 3, and this was shoe 1 and shoe 2. 6.3c, we're going to determine if events are independent or dependent from each other. Let's first write down the formula to test for independence. Remember, we're going to find the probability of A and times it by the probability of B. We're going to test and see if that is the same with the probability of A and B. So what we have to do here is find 3 different probability fractions. I can tell because this P here is one probability, that's a second, and that's a third. So let's read the problem and do it. So a pair of 6-sided dice is rolled. Let A be the event that a 6 is rolled on the first die. B is the event that the sum of the numbers rolled is 10. Are A and B independent? Now, you might have a gut instinct. Independence means this, that the first outcome will not impact the second outcome. Again, here's the first event. A 6 is rolled on the first die. Now, the second event is that the sum of the numbers rolled is a 10. My instinct tells me it sounds like the second event is going to be dependent on what happens in the first event. So the odds are what's going to happen, these 2 are probably going to come back and not be equal. If these are not equal, means they're dependent. If they equal, they're independent. So I'm going to draw out the sample space of rolling 2 different dice that are 6-sided. So here's what our sample space looks like. Here's die 1, here's die 2. Again, 6 and 6 would be 36 different outcomes. Now I'm going to put the words of event A and B in here, and we'll find the probabilities accordingly. So what we're going to first find is the probability there's a 6 on the first die. So if we're just looking at one die, the probability that there's a 6 on one die would be 1/6. And then here the probability that the sum is equal to 10. So that one I am going to go to the grid, and the sum has to be 10, so that would be a 6 and 4. A 5 and 5, and a 6 and a 4 and a 6. So that's going to be 3 out of the 36 in this case. Now let's go ahead and actually simplify this fraction here. The 3 and the 6 can be simplified. I can take a 3 out of here and a 3 out of here. So let's go ahead and do that. And I'm going to call this, when you multiply straight across, this is going to equal 1/72. Now that is the answer to this right here. Let's go ahead and find this one. So this probability is going to be asking me for that the that there's a 6 on the first die, and at the same time the sum is the 10. So if we look at this, we know that the sum of the 10 is already marked on our grid. But at the same time, there has to be a 6 on the first die. So the only scenario that works for that is this one right here. So there's 1 out of 36 for that. So what you do is you compare these two answers. If they're the same, it's independent. If they're different, there's some dependency going on. We can clearly tell here that they're not equal. So these two events are dependent on one another. 6.3d, we're going to find AND probabilities with events that are independent. So if two events are independent from one another, here's the great trick. I do not have to go back here like I did on this problem and do the sample space and count it out. If they're independent, what I am now allowed to do is actually piggyback off of this particular formula here, and what I can do is a shortcut and just multiply two events together or three events together. So if it's a probability of A and B, I just multiply. So let's go ahead and look at the first question. A baseball player has a batting average of .240, which means that he has a 24% chance of getting a hit in each at-bat. What is the probability that the player hits in each of the three consecutive at-bats? So we want to know what's the chances that his first at-bat makes it, and his second makes it, and his third. Notice I said and. When you say and, in most cases you multiply. So what is the probability he makes it the first time? That's the batting average. What's the probability he makes it the second is the same thing, and the third. Really what we just did was 0.24 to the third power. If you simplify that, you're going to get that there's going to be a 0.0138 chance or probability that he makes three consecutive bats in a row. The second question here, a particular location has a 16% chance of snow on any January day, regardless of whether or not it snowed the previous day. This means they are independent from one another. There's no connection. 16% chance of snow. Here's the first question. What's the probability that 2 consecutive days will snow? Well, day 1 and day 2. Again, I said and, so I multiply. The probability of those is 16%. So when you do 16% squared, or by itself, you're going to get that the chances are quite a bit smaller. It comes down to being, in this case, a 2.56% chance it snows in 2 consecutive days. The second part, what's the probability of 2 consecutive days without snow? If it's a 16% chance of snow, what is it without snow? Well, that's its complement. So what's the chance that day 1 it doesn't snow and day 2 it doesn't snow? That would be 1 minus 16% or the 84%. In this case, another 84%. If you multiply those two together, you're going to end up getting that the answer is 0.7056. So it's much more likely it doesn't snow 2 days in a row. In 6.4a, we're going to compute the number of arrangements using the multiplication counting principle. For the first scenario, Caden is hanging 7 pictures on a wall in a single row. How many different ways can Caden hang the pictures? So if you think of it this way, he's going to hang 1, 2, 3, 4, 5, 6, 7 pictures. And you can imagine all the pictures are sitting here on a table. When he first comes over here to grab a picture, there's 7 choices. So he's going to hang one of them here, again with 7 choices. Now he hangs the picture up here. When he comes back to the table for the next hanging, one of the pictures is gone. There's only 6 choices. So he does 6. Again, he comes back to the table. There's now only 5 choices. So then we have 5, 4, 3, 2, 1. If you recognize the shorthand for this, this is actually the same as 7 factorial, or 7 exclamation point. When you simplify this answer, you will get that there's going to be 5,040 different ways for Caden to hang these 7 pictures. The next question here, how many different ways can Caden hang the pictures if a certain picture must be in the middle? So again, let's go back to the table here and determine that there's one picture that must be hung in the middle. So if I do the 7 spaces, 1, 2, 3, 4, 5, 6, 7, the middle picture is right here. And when he goes, and if he knows it's a certain picture, there can only be one choice to put there. So now he goes to fill in this space on the wall. Back at the table, one picture's gone. There's only 6 choices left. And then there'll be 5, 4, 3, 2, 1. So really, again, the shorthand for this, if you look at it, is 6 factorial. The answer to this will be that there's 720 different ways to hang the pictures, if one of them has to be in the middle. Now this next question is a combination of accounting principle and probability together. So here it is. There are 10 girls and 15 boys in a 3rd grade class. The teacher chooses 4 students at random from the class to work on a special project. What is the probability that all 4 students on the committee will be girls? So if you think about how probability works for this, we want to have the option of just picking the 4 girls for the committee out of the entire class. So I'm just going to do here the 4 girls divided by the 4 of the entire class. So if you think about how to do this, what we can do is let's do the bottom of the fraction first. So to do the bottom of the fraction, we have 4 in the entire class, so we have 4 choices that we have to make. So how many students are in the entire class? Well, there's 25 students in the entire class, so there's 25 choices for the first pick. She picks one person to be on the committee. There's now only 24 students left. Then there's going to be 23, and then 22. Then on the top, we're going to pick the 4 girls. Now because we need to have girls on the top, there's only 10 choices for the first space because there's 10 girls in total. So if you pick 1 girl, she can no longer be picked. We're down to 9 girls, 8 girls, and 7 girls. If you multiply this fraction through, you will get 5,040 on the top and 303,600 on the bottom, which simplifies down to about 16.17% chance that on the committee, if you choose randomly from the class, there will be exactly 4 girls. Keep in mind, you could have approached coming up with this fraction a different way. If you wanted to, you could have looked at it this way and said you're going to choose one person, then another, then another, then another. You will get the same answer, but let me show you how it works. For right here, what is the probability that the first person is a girl? What you could say is that would be 10 out of 25 chances that the first is a girl. Now, to pick the second one, you have to be careful. We've already chosen 1 student, so instead of 25, there'll be 24. Assuming you chose a girl, there's no longer 10, there's going to be 9. So this would be 9 out of 24. The third student, assume it's going to be 8 out of 23. And then last, 7 out of 22. Now what we just did here is the exact same thing that we did here, but we just looked at it differently. What we did is this 10 out of 25 is that. The 9 out of 24 is this. So you can think through this problem in 2 different ways and still get the same answer. 6.4, B, C, and D are all grouped together because you can look at these problems in various ways. You need to understand the meaning of factorial, but you can also compute number rearrangements using factorial, or you can use the calculator permutation button. So let's first talk about evaluating what does 10 choose 4 mean. Now there's 3 different ways you can do this. The first thing you might say is if you have 10 items and you're going to choose 4, I'm going to write down 4 spaces. Now from 10 items, your first choice is you would have 10 choices. A permutation, which is the letter P, implies you cannot have any repeats. So this, once we've chosen 1, can no longer be picked. Therefore there's only 9 choices, then 8, and then 7. And if you simplify, the answer you'll get is going to be there's 5,040 ways. Now a second option you could have done is used your calculator. If you go to the Math Probability button and you select the NPR, you can use the calculator. So what you would type in the calculator is this. You would first type 10, then you would go and use a calculator, Math Probability, and then NPR will show up there. And then you're going to conclude it with putting the number 4. And that will kick back with the same answer. Now the third way you can do it is actually to use the formula for this that uses factorials. And here's what the formula is. It says NPR is equal to n factorial divided by n minus r factorial. So if we apply this to this formula, what I would write is I would say 10 factorial is divided by 10 minus 4 factorial. That's going to be 10 factorial over 6 factorial. Now remember what factorial means is you're going to start at this number here and multiply all the way down to 1. Same with this one. So it'll look like this. So we have 10 multiplied to 1 and 6 multiplied to 1. Now what you can notice is on these fractions you can actually cross off. The 6's go to 1, these go to 1s, these all become 1s. So what you're left with is 10 times 9 times 8 times 7, which is exactly what we got in the other method. So any one of those three methods work. Now they're asking you right in here, it says what is meant by 10 choose 4, and what you would do is just write in a sentence structure. It means you have 10 items and you need to choose 4 of them, and that's sufficient to say. This next question, how many 4-letter permutations, again remembering permutation means you cannot have any repeats, can be made from the letters in the word hospital? So imagine that each of these letters is cut up into its own little pieces and put on a piece of paper. So if you notice, there's 8 unique letters. Again, imagine they're each on their own piece of paper and in a hat. And we're going to do a 4-letter permutation, so I need to make 4 choices. If this is our hat over here, when we first put our hand in and draw out a letter, there's going to be 8 choices, so that's what's 8. Permutation means I don't replace it, so when I go back in here, there's only 7 choices, and then 6, and then 5. If you multiply these together, you're going to get 1,680. So there's 1,680 different letter combinations you can make. Now, these letter combinations may not make sense and be exact words. This next one, how many 4-letter permutations can we make? Again from the word hospital, but this time we're not going to be using the letter P. So this time, imagine what's in the hat, there's only going to be 7 options. So when you have 4 spaces, again, if you think about it, we put our hand in there, there's only 7 choices, and then 6, then 5, and then 4. This simplifies to giving us 840 different possible string combinations of letters. 6.5a, we're going to use contingency tables to compute percentages involving categorical variables. So here we have categorical variables. It looks like the city and about the languages that people speak. And it's called a contingency table because it's made up of data about categorical variables. And what it is the number of people of age 5 and over who speak various languages at home in the selected U.S. cities back in 2006. Keep in mind all the data here is listed in thousands. So for example, in Chicago, the number of people that spoke other languages was 287,000 people. First question. What percent of the people living in Chicago and New York combined spoke languages other than English at home? So what I would do for this is identify we're looking at just Chicago and just New York. In the way I see it, when you read this, it says what percent of the people living in Chicago and New York combined. Stop right there. That's the group that we're looking at. So what you want to do is tally up all of these pieces of data. Those 6 pieces of data are going to be the bottom of your fraction here. On the top of the fraction, it says here, they spoke languages other than English at home. Those that spoke other than English would have been Spanish and the other languages. So the 4 red dots go on the top. When you do that, here's what you get. The 3 red dots total 4,583. The 6 numbers is 10,177, which simplifies to about 45.03%. Now this question asked what percent. This next one asks find the probability, which is really still means find the percent. So now find the probability that a person age 5 or older living in any of these cities spoke only English at home. Now the table is everyone 5 and older. So if you again read this, this is first going to tell you the bottom of the fraction. I want a person age 5 or older living in any other cities, and I'm going to stop right there. That number is going to be the bottom of my fraction. On the top of this fraction, I want the people that spoke only English at home. So let's go ahead and tally up everyone in the table, and then we'll add up just the English speakers. So what we're going to put for the top of the fraction is going to be these four totals here. When you do that, here's what you get. The total table adds up to 14,186 people if you add up all this data. Just these four in the yellow, which is just the English people, is 7,342, which gives you about 51.8% probability of me randomly picking someone who just spoke English at home. The last question. Find the probability that a person age 5 or older living in New York City. I'm going to stop right there. That's the bottom of my fraction. So if we isolate just those living in New York City, we're just looking at this for the bottom of our fraction. Of those people, they speak Spanish or another non-English language. So from there, I want this value and this value on the top. When we do that, we will get that there are 7,638 people in New York. Those that do not speak the English are 3,656, which gives us about 0.47866 chance that we randomly select someone that speaks Spanish or another language in New York. Learning Objective 6.5b will not be on the test. 6.5d, interpret from a row percent or column percent table. Question is the following a row or a column percent table? How do I know? This talks about the person's wealth, if they're rich or they're poor, and then their state of mind, are they happy or miserable? If you take a look at this, hopefully you can tell this is a row percent table. Remember, rows go left and right, columns go up and down, columns hold buildings up. That's how you can tell because they're vertical. 75 and 25 is 100, 56 and 44 is 100. So again, it's a row because it totals to 100 by the rows. Is how we know it's a row percent table. 6.6a, calculate probabilities using the conditional probability formula. Let me write that down first. What the formula said is the probability of A given B is going to be equal to the probability of A and B over the probability of B is how the formula works. So what they're doing here, they have an experiment, events A and B. The probability of A is 0.5. The probability of A and B is 0.2. Find the probability of B given that A happens. Notice this is in a slightly different order than this standard format, so I'm going to write this accordingly. All you need to do is imagine taking this and do a 90-degree turn on it. When you do that, the A is the bottom of the fraction. So the formula we need to find is the probability of B given A. That's going to be equal to the probability of B and A over the probability of A. Now they already gave us the probability of A, it's 0.5. The probability of B and A can be written as the probability of A and B. It's the same thing, that's 0.2. So it's a very simple problem. It's just 0.2 over 0.5, which simplifies to 0.4. So there's a 40% chance that event B happens given that A already took place. 6.5c and 6.6b are very similar, so I'm going to put them together. I'm going to sketch a probability tree diagram and find probabilities. And then we're going to calculate probabilities from the tree diagram. So let's go ahead, read the problem, and set this up. So I just turned 16, so I'm going to take my driver's test. There's a 70% chance I can take my test today. If that doesn't work, then I'll take it tomorrow. If I take the test today, then there's an 85% chance I will pass. If I take the test tomorrow, there's a 90% chance I will pass. Sketch the probability tree diagram depicting when I take the test and the possible outcomes. So it's first going to start that I take the test today or tomorrow. So here I am, I'm getting ready to go take my test, and it's either going to happen today. If it doesn't happen today, it happens tomorrow. Now the chance that it happens today, it says, is a 70% chance, so I'll put 0.70. So that means there's a 0.3 or 30% chance it happens tomorrow. Now if I take the test today, it says here I have an 85% chance of passing. So I'm going to do this as it's a test. I'm going to do plus I passed negative, I failed. So on here, when I fill in the tree, what I'm going to complete is that there's an 85% chance I pass it, therefore there's a 15% chance I fail. If I take the test tomorrow, it says here there's a 90% chance that I pass. So that's my plus, and then my negative is just its complement. So on here, I'm going to put 90% chance, and therefore 10. Now what I did is just created 4 strings, 4 different possible outcomes. I test today and pass, I test today and fail. I test tomorrow and pass, I test tomorrow and fail. Notice when I read each string, I said the word and. When you hear the word and, the key here is to multiply. So what I'm going to do is figure out the answer for each string. And all I have to do is I'm going to take 70% times this, 70% times this, and do that for all the strings. And here's what you'll get. So the various strings give us these different probabilities. Now do make note, if you were to add up all of these probabilities, it will actually come back to the 100%. So now let's answer our first question. What is the probability that I pass my test on either day? Well, to do this one, you just want to go and find the branches of where I passed my test, and it says either day. So if I did, I would pass my test this day, or I would pass my test this day. Keep in mind, I just said the word or. When it's this or that, you're going to add them together. So here I'm going to add the first probability and that second probability together. When I do that, I end up getting that there's going to be an 86.5% chance I pass my test on either day. So I'm pretty happy about that. The second question, given I pass the test, what is the probability it will be tomorrow? So this is a given statement. Remember on that, we've just shrunk down the sample size. So I need to start and narrow down my fraction to be given that I passed the test. So I'm going to find all of the branches that say I passed the test. And that would be this branch and this branch. The total of those two, which we actually already found, is going to be the bottom of my new fraction. So I'm actually only looking at the 86.5% of the group. Now it says here, what is the probability it will be tomorrow that I pass? So when you look back over here, the one number that deals with tomorrow is the 0.27. So that's what goes on the top, is the 0.27. When you simplify this fraction, you're going to get that it's about a 31.2% chance that given I pass the test, what are the chances it actually happens tomorrow? So tomorrow, it's a 31.2% chance it happens, is the answer. This second question is conditional probability. The first one is just standard probability. You can answer both of them by making branches, which makes it a lot easier to see. 6.8a, we're going to compute expected counts of events. Here it says each of the whole numbers from 1 to 8 is written on an index card, and they're placed in a bag. The card is drawn from the bag, the number is recorded, and it's put back in the bag. This process is repeated, so there's a total of 6,600 cards drawn. By the way, this table here shows you the outcomes of that experiment. First question is, what is the expected number of times the number 5 will be drawn? Keep in mind the formula for expected count is n times p, where n is the number of times the sample was taken or the experiment was done, and p is the probability of drawing a 5. So what we're going to write here is 6,600. The probability of drawing a 5 from 8 cards is 1 out of 8. When you multiply this together, you're going to get 825. So we would expect the number 5 to show up 825 times. Now this question here, if the result of the experiment were as follows, what might you conclude? What we're going to notice here is the number 5 actually showed up 1,500 times, which is quite a bit more than what we expected to happen. And we did this experiment many times. So on this, the law of large numbers took place. We did this experiment enough times. So what we could conclude is this: there's something wrong with that index card. Maybe the card is larger than the others. So if this were the case, we might be drawing it more likely than what we should. Maybe there's a tear in the card, or it has an earmark on it, so we grab it more likely. Let's go to 6.8b, which is understanding the law of large numbers and the law of averages. We're going to piggyback off the exact same question, and here it is. Could you decide if the 8 cards are equally likely to be drawn if the 5 is drawn 4 times in the first 20 draws? So let's actually do this. What we might want to do is come up with the expected count was. What we know is that they said in 20 draws it actually happened 4 times. So what did we expect to happen? Well, again, expected count is n times p. We did this experiment 20 times. We know the probability is 1 out of 8. If you simplify this, you're going to get that it should have happened 2.5 times, but it actually happened 4 times. Again, there's a discrepancy. But did we do this experiment enough for us to conclude that there's something up with this card? Keep in mind, back in this problem, we did the experiment 6,600 times. Now we just did it 20 times. We're seeing a similar result in that the actual count is higher than what we expected, which is what we saw here. But keep in mind, we really have not hit the law of large numbers. And you would have to say here, no, we probably couldn't. We need to really be cautious, and due to the law of large numbers, we cannot make a conclusion that there's an issue with the 5 card. We really should do the experiment more times, something more similar to up here.